Welcome to my talk, Large High-Resolution Displays Interacting with Information Beyond the Desktop. First of all, I would like to introduce myself. I'm Lars Lischke. I'm Assistant Professor for Human-Computer Interaction at the Vrije Universiteit Amsterdam in the Netherlands. Before, I studied computer science at the University of Stuttgart in Germany and at Chalmers in Gothenburg in Sweden. Then I did my PhD in human-computer interaction under the supervision of Albrecht Schmidt, also at the University of Stuttgart. After my PhD, I joined as a postdoctoral researcher at the Technical University in Eindhoven, looking there on prototyping large IoT projects. But now I would like to focus on my research in looking on interacting with large high-resolution displays. So, in a lot of different visions and future scenarios, we see actually extended screen space as well as displays or extended display space at workplaces for better interaction with large data sets. However, we don't see them a lot of in the current daily work environments. To actually understand how we design such displays with a high usability that then we can benefit from seeing more information at the same time, I will talk on this talk about three different aspects. So first of all, I will talk about understanding people seeing information on large and high resolution displays. Then I will talk about adequate input technologies for such displays. And finally, I will briefly discuss challenges in designing graphical interfaces for these displays. Now we are starting with understanding people. So when we look on environments where even today people use a lot of display space, we can use these environments as a good study environment to actually understand current challenges. Here you see a picture from a control room of a public transport company in Germany. In this control room, 6 such working desks are always in use to control all traffic in the city. Every desk is equipped with 6 full HD desktop screens. 2 of these tables are also equipped with 6 additional screens to monitor public train traffic in the city. Furthermore, all screens facing a wall-sized display in front of them. In a contextual inquiry, we were actually interested to understand how users interact with those display environments and also how they interact with each other in a collaborative setting. So over 3 shifts, we observed how work is performed in this control room. Thereby we choose different shifts, so morning rush hours, night shift and a weekend. So what we actually saw is that users in these control rooms, they work with a lot of different and isolated systems. They have to copy information manually either on paper or between different applications to process all required information. In interviews, we figured surprisingly out that even though they use already a lot of screen space, they would like to have much more screen space to be able to monitor a lot of processes simultaneously. This is quite surprising because when people sit the first time on such a desk, they said they would be totally overwhelmed by the amount of information they can see in parallel. However, we also saw a number of challenges for working with these display environments. So, for example, visual content did not always appear on the position the user would expect that it would appear. So, for example, notification popped up on different screens than the user worked before, or another window opened somewhere else and the user had to manually perform a visual search task to figure out where the window is actually appearing. Furthermore, shifting the input focus was quite challenging, so they were not always aware of which window is activated when they were looking somewhere else, or they had quite some challenges to rediscover the mouse cursor when they switched from one window to another. But now, in the beginning, we were also interested in understanding what does actually high resolution means for our daily work with digital devices. And as we all know, the pixel density on all devices is steadily increasing, but actually we wondered about the influence of the screen resolution on our performance. So we conducted a user study using a tablet, simulating 4 different screen resolutions, starting from 90 pixels per inch over 120 and 180 pixels per inch up to almost 360 pixels per inch, which is the full resolution of the tablet device. We simulated the screen resolution always on the same device to keep all other screen parameters identical between the conditions. So, for example, that in all conditions the backlight was the same, the refresh rate was exactly the same, things like this. We simulated the screen resolution by simply lowering the resolution of the shown images during the study. We used 3 different tasks involving common visual content used on tablets, but also on all other kinds of screens. So we had an image search task, we had a word counting task, and video analysis task. I will explain these tasks in a second. We invited 16 participants to our lab to perform all the tasks on all 4 different conditions. So in the image search task, we showed 32 images on a specific topic. In the center of the screen, there was one object shown as a larger object, and the same object was appearing also in one of the other pictures. And here, participants had to search the smaller picture with the same object and then select this object by clicking on it. We repeated this task 5 times per condition. In the word counting task, we showed common fairy tales or snippets of these, about 300 words per task, and then asked participants to count specific short English words such as the or and in the shown text. We repeated this condition 3 times, this task 3 times per condition. And finally, we had a task on a video analysis basis. Here, participants had to count how often balls were thrown around between different people shown in the video. Again, we repeated this condition 3 times per condition. We measured over the whole experiment the distance between the user's eye and the tablet. By an optical tracking system, we asked participants to hold the tablet all time in the hand while performing the tasks. We measured the task completion time automatically through our apparatus and also counted the errors. After each condition and every task, we asked also all participants to rate the mental effort and the perceived media quality on standardized scales. We saw in the results that the perceived media quality was perceived as differently, so the higher resolution was perceived as higher quality in all different conditions and tasks, besides the video analysis task. Here it might actually play a role that showing high resolution videos on the tablet might cause also other effects such as image delays, which might influence the results. But in particular for text-based tasks, the high resolution was perceived as better in quality. When we look now on the perceived mental effort, we only saw significant differences between the conditions for the text task where people had to count specific words. Here, the effort increased when the resolution was low. So actually what we saw here in this experiment, that higher resolutions are perceived as better in quality, but have only an effect on the mental effort for text-based tasks. And furthermore, the resolution did not influence in our experiments the performance of the participants in all tasks. So there were no significant differences in terms of task completion time or error rate between the different conditions. However, as a limitation of this study is that the study was relatively short and was completed per participant within an hour, so we do not know if the effect would be different if we would ask participants to work over a full working day on low resolutions. On the other hand, this shows that we can also assume in other short stories, looking now on large displays, that the exact resolution does not play a too important role. So we were now interested in comparing the effect when analyzing data sets in a team if you do this on a small tablet or on a wall-sized display. What you see here is a health data set visualized by common visualization software where you can detect different trends and correlations between different informations. So we asked in this study half of our participants to analyze the data set on a tablet and the other half of the participants to analyze the same data set on a wall-sized display. In both conditions, we used standardized visualization tools for such data sets. The results of our study here revealed that using the large display was mentally less demanding for the participants. However, using the tablet was beneficial in terms of turn taking, so the participants shared more the interaction with the data set on the tablet than on the large screen. This might be due to the fact that it's quite easy and natural for the participants to share together the interface when they can touch the interface lying in front of them, and it's more complicated if they use a regular mouse and a keyboard in a collaborative setting. In both conditions, the understanding of the dataset helped the participants to agree on sharing own personal data for research purposes. So we can assume that making users aware of actually what we can do as scientific community with personal data increases the willingness to share personal data for such projects. Now that we saw actually that having more screen space to analyze complex data sets, when we compare a very small display to a very large display, we were also interested in can we find this effect more detailedly when we vary the screen size. Here you see a prototype where we actually showed conference proceedings on a 4-meter wide display. In a study where we varied the screen size, we asked participants to search for specific images or text elements in the whole proceedings. Here we varied the screen space, so in the condition where the users used the full screen, they had no need to scroll at all. However, they saw the same amount of information but had to scroll in the smaller conditions. There were no significant differences in terms of task completion time independence of the screen size. If the search target was more at the back of the document, then participants needed longer to search, but this was not in relation to the screen size. So here we can argue that participants are not visually overwhelmed if they see a lot of information at the same time. When we look on the perceived workload, also there's not much of an influence on the screen size. However, if the display is wider than 2.5 meters, participants start to walk in front of the display, which creates more physical demand. However, here it's not clear if this physical demand cannot also be an advantage when using such displays, such as preventing too long sitting in front of the display, getting physically more active, which can lead to feeling more engaged and less tiring when performing work. When we now look into how people actually walk in front of the displays, we were interested in understanding if we can influence this in different kind of ways, and then also how this influence can be used in different kind of settings. So we implemented a multiplayer large display version of Pac-Man, so called Pac-Mani. Here we had all the elements from classical Pac-Man, but just on a 4-meter wide display. We had 2 players, so for the collaborative game playing. We had classical dots to collect, and we had power pellets which could be used to be protected from the ghost to be not eaten. We had the ghost trying to eat the players, and as an addition to the classical Pac-Man game, we had portals which allow, if you walk over this one, to appear on the other one. And this enables us to foster more movement of the participants and quicker movement from one end of the game to the other end. The game was controlled by smartphones, where we had a web application which allowed the users to navigate the gameplay on the map. We had 2 different playing modes, one collaborative game mode where both players together had to collect 400 pack dots and collect 24 power pellets and use the portals 12 times. They shared also 10 lives. In the competitive mode, simply they played against each other and had to be quicker than the other player in collecting 200 of the pack dots, in collecting 12 power pellets, and using the pack portals 6 times. Here every player had 5 lives. We invited 12 pairs to play both conditions for 20 minutes. While they were playing, we tracked their motion in the room via an optical tracking system, and after every condition we asked them to fill out the social presence gaming's questionnaire. Luckily, both conditions were perceived as different, so in the collaborative mode they felt more empathy and also more involvement than in the collaborative mode and the competitive mode. The most surprising result for me was actually here that the distance between the players in the different conditions was significantly different. In the competitive mode, the players stood more closely together than in the collaborative mode. This can be also explained by game theory. Here, the Nash equilibrium states that competitors try to be as close together as possible to simply prevent the other one having an advantage over their self. This is something you can also see, for example, with gas stations. They often cluster at the same point simply to see all the same customers, to not give the other one an advantage. Furthermore, interesting here is that we can clearly see the proxemic zones defined by Hall in the 60s. So in both conditions, participants try to avoid approaching the other player in the intimate zone and closer than 40 centimeters. In the competitive mode, players stood in the personal zone between 40 centimeter and 1.20 meters, while in the collaborative mode they spread out and mostly were distance about 1.50 meters to the other player. Furthermore, we saw that the competitive game foster more movement of the body movement of the players than the collaborative mode. Here, participants walked about 10 meters more than in the collaborative game mode. Hereby, this is then also interesting to think about how we actually can use this in different kind of settings for large display interactions. So, for example, if you think about a public display game in public space, for example, at a train station, you might not want the participants or users walk too much to not distract others. So you might think about how to limit the interaction in a way that they don't walk too much, while in other setups it might be interesting to foster more movement for different kinds of reasons. In the next step, I'm also interested in actually how we can use these results for not only gaming environments, but also for exploring datasets. Now I would like to move on to input techniques for large displays. As you already saw, and there are a lot of challenges regarding common input techniques from desktop environments and a lot of other possibilities to perform input. However, there is no standardized input technique at the moment for wall-size displays, which makes it always complicated to design well-suitable system for interaction. First of all, I would like to show you an example where we used handheld tablet devices for personal interaction and a wall-size display for shared view on a dataset in a team to explore this dataset to detect trends. Here on the personal device, people were able to select different keywords, filter for specific things, and have a different map view than on the shared display, but then they were also able to push information to the shared display and discuss with the colleague what they actually figured out as a trend. Here we used geolocated Twitter data to detect trends spreading in time and also in space. And again, I have a short video. We conducted a user study where we compared this to a classical desktop setup. Here in this video, you see how participants can analyze flu spreading in the United States 2013. In this study, we then saw actually that the perceived workload was lower using the wall-size display in addition to the two handheld devices instead of using only one shared desktop environment. As you already saw in the talk, performing pointing tasks on wall-size displays is quite challenging, and there's a lot of possibilities to improve pointing tasks on wall-size displays. Already 2000, Chum-Tsai et al. Proposed using magic pointing to perform pointing tasks with the mouse more efficient than in classical environments. For magic pointing, the eye of the user is observed by an eye tracker, and by pressing a particular button on the mouse, the user can simply warp directly the cursor position to the current gaze position. And thereby the user don't have to navigate by navigating the mouse over the space to the target, but simply can look at the target, press the button, and then have the cursor close to the target already. In the original study, the authors assumed that this might be particularly beneficial if the display space is really large. So our approach here was we used a head-mounted eye tracker, which allows us to observe participants' eye also when the head is moved to see the other end of the screen. And this eye tracker also has a world camera to actually then map the gaze position to the screen position. Therefore, we used the marker you can see here on the pictures. We conducted a lab study where we asked participants to perform pointing tasks using the mouse only, and also to use magic pointing, so with the assistance, select targets with the assistance of the eye tracker. We invited 12 participants. Both performed the task in both conditions. The results of the study were quite positive, and we were quite happy about the results. So there was a significant shorter task completion time when participants had the additional support of the eye tracker, and also the perceived workload was significantly lower. Then we had a more detailed look on the results in terms of also how they distributed over the screen space. So where actually has the addition of magic pointing in positive effect as an input modality. What you can see here, the effect in the center of the screen is quite small. However, on the left side, the mouse only was faster than having the support of the eye tracker on the right side. We assumed that this might actually caused by using a monocular eye tracker, which only observes one eye of the participant and therefore has a less precision when the user is looking in one of the directions. Therefore, to actually prove this, we had also a look on the distance between where the cursor was warped to and also the distance between where the cursor was warped to and the target position. And as you can see here, in the area where the mouse only condition outperformed the magic pointing condition, the distance was much higher. So what we actually did, we improved our prototype. We used an even wider screen. We used the binocular eye tracker observing both eyes of the participant, and we used a standardized pointing task. We had, again, as independent variables, either the input conditions or easily using the mouse only, or having the additional support of magic pointing, where participants were able to warp the cursor position directly to the gaze position. We had 4 different target sizes, and we had 4 different amplitudes or distances between the targets. We invited to our lab study 35 participants. Surprisingly, in this study, none of the magic pointing conditions outperformed the mouse-only condition. When we look now more detailedly on the differences between the tasks, we find an explainable reason for this. So in the second study, the setup looked like this. All the time both targets were visible, and one target was lighted up, so the user had to click on this one. As soon as the user selected this target, the other target lighted up, and the user had to click on this target. During the whole study, the participant was aware of the cursor position and of the position of the next target. While in the first study, the target appeared randomly on the screen, the user had to select this target, and as soon as the target was hit by the user, the cursor was reset to the starting position, and the new target randomly on screen appeared. Here the user had to search again where the cursor is now and then click on the target again. So we can conclude from both studies that eye tracking can support target selection on large displays. However, it helps only in terms of reducing the workload and performing this task quicker if a visual search task is involved in the process. So it's quite hard to improve the pure motor task of target selection over the common mouse interaction. Furthermore, in interviews, participants stated that the additional support of the eye trackers helped them to focus more detailedly on the current task. Now I would like to shift to another input device. So assuming that when you interact with a large visual data set, you might be not able to focus on the input device itself, and you might be not able to see what you're directly influencing. You might just see, for example, the effect of the value change, but not the value change itself. Here we wondered if additional haptic feedback could help to perform precise input. What you see here is a linear slider, as you might know from different devices, But in addition, this slider can be actuated by a motor controlled over an Arduino. Thereby, we can provide some force to move the slider in a certain direction or support the movement of the user by moving the slider automatically in the same direction. Thereby, we can present haptic feedback patterns on the slider scale. What you see here and what we implemented for the next coming study, we simply introduced knobs where you can actually feel specific values by having a higher resistance on particular values. Our assumption was that the additional haptic feedback will not influence the task completion time and also will not have an influence of the accuracy when there's direct visual feedback. Simply our assumption is that if there's visual feedback, we are so trained to visual feedback that we don't really perceive the additional haptic feedback and can simply provide very precise input. However, we assume that if there's no visual feedback from the input device, the additional haptic feedback helps the user to perform input more accurate. Furthermore, we assumed that the combination of haptic feedback and visual feedback might result in a higher mental effort. So again, we conducted a repeated measure study with 3 different independent variables. So we used the device, so we had our physical slider, as you already saw. We printed therefore a 3D case, it's easy to touch. And we compared this to a software slider displayed on a regular Android tablet. We varied the visual feedback, so either the device itself was visible and also on the output device there was visual feedback provided, or we covered the input device so that the user was not able to see the input device itself, and we did not provide visual feedback on the output scale. Furthermore, for the tangible device, we either had our additional haptic movement feedback, or we had simply only the physical slider, which was tangible. We performed again a target selection study where participants had to select specific targets indicated by a green arrow on a larger display. Every trial started from the left, and then the user had to move the slider knob to the right, and we repeated per condition this task 32 times. When we look now on the results, we see that there's a difference between the task completion time when there's no visual feedback. Here, the task completion time was higher when we provided additional haptic feedback but had no visual feedback. So our first hypothesis was only partly correct. When we look now on the accuracy or the error of the input, we see that clearly helped the user when there was no visual feedback provided to have additional haptic feedback. Also, we see here, obviously, when there's visual feedback, the error is much smaller. And finally, we had a look on the perceived mental effort, and there were no significant differences between the input modality and the feedback in terms of mental effort. Only what we can see here, if there's no visual feedback, then the effort is perceived as higher. So we can say or conclude from this study that additional movement resistant feedback can help to explore complex data sets for the user and to perform more precise input when the device cannot be viewed simultaneously as the input is performed. In our study, we had a very simple 3D printed case for the slider, and in the next step it would be interesting to explore different kind of form factors for the slider device. So it's also a possibility to include multiple sliders to have multiple dimensional input in one device, or having the device placed on the table, or having other form factors. Furthermore, the movement resistant feedback pattern can be programmed freely and any pattern can be implemented. In this study, we had a very simple pattern, and it would be interesting to have more complex feedback patterns on the slider device itself. So now finally, I would like to move on to graphical interfaces and how we actually can understand how we should design graphical interfaces if we have work environments for large high-resolution displays. Here we conducted a study with a low-fidelity prototype where we invited participants to arrange their own working desk, assuming that the card boxes shown in these pictures would be large displays. We provided 4 of these cardboards and different kind of mounts around the working desk and asked participants to arrange their working environment and then also place content on the screen space. We saw that when participants, assuming they would work alone, they would have in the center an area where they would perform focused work. On the left and the right side, they would place additional information such as web browsers or documents where they look up information, while all communications and notifications would go to the upper area, so-called C in this image, allowing them to view whenever needed all incoming events, but being not distracted while performing focused work. When they assume they would collaborate with another colleague on their working desk, the personal notifications and communications would disappear and the focus area would expand to the upper part. Simply, all participants assumed that the colleague might stand while discussing a specific problem, and thereby it might be useful to use the larger screen space also above the focused area. When we had a look on the different screen arrangements, we saw that all the arrangements were actually symmetrical. However, not all of the participants would like to have one plain display. Some of them separated parts of the display simply to have also physical separation of their task and their work environment to be not distracted and have a more focused area. So actually this was my overview about large display research. So I showed you examples of how we need to understand how people interact with large displays. I showed you different design probes for different input techniques for large displays, and I give you a short example of research on graphical user interfaces for large displays. In particular, for such graphical interfaces, it is important to understand how we can automatically support the user in arranging content, simply because the display space is so large that it might be not time efficient possible to arrange all content manually. So as a short outlook, I'm interested in future to explore how we can design better interactive data visualizations, not only on large displays, but in all kind of different environments. How we can provide better access to information. I see here a huge possibility in designing context-aware systems, understanding the state of the user, and adapting then the shown content to the state of the user. Here, possibility is to also activate the user to become physically more active while working on an office environment. Thank you very much for your attention, and I'm happy about your questions. Finally, I know at the moment this is not possible, but I hope that we will go back to a somehow normal working style in the future. So if you're interested in working with me on any interesting human-computer interaction topic, I'm happy to have you around in Amsterdam. So here you can see our campus environment. We recently moved to a new computer science building, and I'm happy to discuss possible projects with you. Thank you very much.